Hello and welcome back to the video lecture series for ECE-340. I'm your instructor, Dr. Bradley Duncan. Today we're going to be looking at random processes that pass through fixed linear systems. Unlike our discussion for nonlinear systems, for linear systems we're going to be able to get some closed form input-output relationships that apply to all linear systems. And before I move on, I want to discuss this word fixed just a bit. Some of you may have heard in the past discussions of linear time invariant systems. That's exactly what I'm talking about here. Linear systems that are fixed in time or that are time invariant. Time invariant, okay? Once I solder all my components together, they don't change, okay? So, let's talk about what we mean. Here's my fixed linear system, time invariant linear system. My input is going to be random process X. My output is going to be random process Y. My linear system is going to have an impulse response, little h of t. And the Fourier transform of an impulse response equals what we call the transfer function. And my output y can be written as a convolution integral, the convolution of my impulse response and my input. All right, you'll notice that this is a convolution integral. Don't panic. In almost all cases, I'm not going to have you do any convolution integrals. We'll instead use our understanding of Fourier transforms to make our lives a little bit easier. All right, so some shorthand notation here. Y of t as a random process. Y of t is going to be my impulse response convolved with x of t. That little asterisk stands for convolution. All right? So let me put some boundaries on what we're going to be discussing. First of all, we are going to assume, for the time being, we're going to assume that my impulse response is real. That will allow me to simplify some of the math, but the results will be general. Meaning that the results that I get at the end of some derivations today will be applicable to systems that even have complex impulse responses or transfer functions. Second thing is we're going to assume that my input and output, x of t and y of t, are at least wide sense stationary. We are going to ignore any system delay. All right, we're either going to assume that the output responds instantaneously to inputs, or we're simply going to ignore any delay. And we're going to assume that we're looking at steady state conditions. All right, we're going to assume that the input has been applied for a long time and that any transients that may have resulted or have died out. Okay? All right. So really what we're going to try to get a handle on today is some interesting characteristics of the output given knowledge of the input. Really what we want to do is we'd like to find We'd really like to find the mean, making my funny muse again. We'd like to find the mean of y. We'd like to find maybe the mean squared of y. We'd like to find the autocorrelation of y. And maybe we'd like to find the power spectral density of y. All right. Remember, if I have either the autocorrelation or the power spectral density, I can find the other by either a forward or inverse Fourier transform process. That's the Wiener-Kinshine theorem. If I evaluate my autocorrelation, for example, at 0, that gives me the mean squared value. If I evaluate it at plus or minus infinity, that gives me the square of the mean value. From there, I can find the standard deviation or variance. Okay? Lots of fun things I can do. Let's begin by finding the mean of my output. That's the simplest thing that we can do. So the mean of y, that's the expectation of y, equals the expected value of this convolution integral. Okay? So y is just the convolution of x with my impulse response. All right? So the only thing that has randomness here is my input random process x, so I can move the expectation inside of my integral. And so this gives me integral from minus infinity to infinity. Expected value of x of t minus tau. H of tau d tau. But now I'm going to remember that I'm considering only at least wide sense stationary random processes. So the expected value of x of t minus tau is just the expected value of x, and that's the constant value mu of x. And since it's a constant, it can come outside of my integral. That's that. Okay? All right, let's move to the next page and finish this up. Now, recall this. The transfer function of my system is the Fourier transform The transfer function is just the Fourier transform of my impulse response, and the integral that I've written here is the definition. It's the defining integral for the forward Fourier transform. That's the defining integral for the forward Fourier transform. Okay? Well, if I evaluate my transfer function at 0, I get integral from minus infinity to plus infinity of h of tau d tau. And that's what we had at the bottom of the last page. So this is the DC gain, if you will. All right, the DC gain, it's my transfer function evaluated at 0 frequency. So that's my DC gain. And it's also equal to the area of my impulse response. Okay? So plugging that into the result at the bottom of the last page, what I get is that the mean of the output equals the mean of the input times the DC gain of my linear system. That's one general result. Okay? So as a simple example, what if we have a little RC low-pass filter? And my input is x sub t. That's resistor R1, resistor R2, some capacitor. Y of t is my output. All right. Well, at 0 frequency, my capacitor is going to be an open circuit. At omega equals 0, capacitor is an open circuit, and so the transfer function is just found through voltage division. All right, and so for my simple RC low-pass filter circuit, this is a low-pass filter. At high frequencies, that capacitor becomes a short circuit, and so the output goes towards 0. All right, so it's a low-pass filter. So for this guy, my mean of my output equals the mean of the input times R2 over R1 plus R2. Simple enough. Okay? All right. What about correlation functions? What we're first going to do is we're going to look at the cross correlation of the input and output and use that to find the autocorrelation of the output. So, cross correlation. Hyphen in there. It's supposed to be a hyphen. I'm going to do cross correlation first because I need cross correlation, turns out, in order to get access to autocorrelation of the output. All right. The cross correlation is this. The expected value of x times the shifted version of y. Okay? And plug this in. I get x of t times the convolution. Alright, and alpha here is just some arbitrary integration variable in order to set up the convolution. So that's just, sometimes it's just called a dummy integration variable. Alright, and to get to this point, recall that y of t, my simpler convolution integral is just this. That's just straight simple convolution. And what I really need is y of t plus tau. And so I just plug in t plus tau everywhere I had a t. All right, that's all I do. X of t is delayed, but the impulse response is not. That's what this is all about. Okay? Okay. Now, once again, you'll notice that my random process right here is not a function of my integration variable alpha, so that can come inside of my integral. And the only thing that has randomness associated with it is x of t and its shifted self. So that allows me to rewrite my cross correlation the following way. Okay? What I did was I moved my random process x of t inside of the integral and also moved the expectation inside of the integral. This then is h of alpha times the autocorrelation of x evaluated at tau minus alpha. All right? Remember, anytime I find the expectation of x multiplied times x at some later instant in time, that's an autocorrelation function. So this expectation is really an expression of autocorrelation. And you'll also notice that this last result, the second line on this page, is a convolution integral. This is the impulse response convolved with the autocorrelation. All right, the cross correlation for a linear system, the cross correlation of the input and output is simply the impulse response of my linear system convolved with the autocorrelation of the input. All right, so another thing we can do is, this is a result that we're going to use in order to find the autocorrelation of the output. So hang on to this for just a minute. But we could do this. We can take the Fourier transform of both sides. Take the Fourier transform of both sides. And we get that is a general result, and this thing here I haven't discussed before. It's known as a cross spectral density. All right, and my cross spectral density, I'm not going to get too deep into this, is just the product of the transfer function times the power spectral density of the input. This is a general relationship, and my result a little higher. That's a key result, and this one is also general. Okay? All right. So, like I said, what we're really trying to get access to is the autocorrelation of the output, and I'm going to need this cross-correlation term to get there. All right. What's the autocorrelation of Y? Autocorrelation equals the expected value of Y multiplied times a shifted version of itself. And Y is expressed through a convolution integral. This is all multiplied times integral from minus infinity to plus infinity h of alpha 2 x of t minus, or t plus tau minus alpha 2 d alpha 2. There. All right, so y is related to x through convolution. Make sure I've got all my parentheses and such closed. Yeah, looks like I do. Okay, well, I'm not going to do all these steps here. As they say in professor speak, the steps are straightforward but tedious. It takes me about a page of math to go through the process of performing the steps of this double nested integral. I'm not going to do it as part of the video lecture. I'm going to make a handout for you and provide that for you and give you all the steps separately. So I'll say here, see handout. See handout for the details. And the results, after several steps, are my impulse response evaluated at negative tau, convolved with my cross correlation term. All right, but my cross correlation, and that's why I needed this earlier, my cross correlation can be written as h of tau convolved with the autocorrelation for x. Okay? So there's nothing. I've said so far that I'm assuming that my impulse response is real, just to make the math simpler. But there's nothing that I've said so far that implies that the impulse response must be symmetric about the time equals 0 axis. However, if I convolve the impulse response with a mirror image of itself, I get a result that is even in tau. Okay? If I take an impulse response and I convolve it with a mirror image of itself, I get something that's even. I know that autocorrelation is always even, and I also require that my output autocorrelation be even. If I take all of this, which is even in tau, and multiply it times another function that's even in tau, I get a result that is even in tau. So that's good for us. And so once again, this is a general result. Let me summarize it here. I'm running out of room. It's going to be h of minus tau convolved with h of tau convolved with r x of tau. This is all general. That's a general result. Okay? All right. Well, what about power spectral density of the output? Power spectral density is actually going to be more useful to us because to get access to the autocorrelation of my output, I've got to do a double convolution involving a mirror image of my impulse response. Oh my goodness, I don't want to do that. I'd rather use some Fourier transforms, move into frequency space, and make my life a little bit easier. So what about the power spectral density for my output? That's supposed to be a question mark. All right. First of all, let's notice this. Oops, that's supposed to be a dt. All right, this is a slightly different version of the defining integral for the forward Fourier transform. Okay, that's a forward Fourier transform. And by forward Fourier transform, what I mean is I'm moving from the time domain into the frequency domain. The inverse Fourier transform moves from the frequency domain to the time domain. All right. So what about this? The Fourier transform of h of minus tau will equal the integral from minus infinity to plus infinity of h of minus tau. And this is getting me access to part of the problem on the previous page for the I'm going to take the Fourier transform of the autocorrelation of the output, and that involves taking the Fourier transform of h of minus tau, trying to get access to what that will look like. So proceeding, I have the integral from minus infinity to plus infinity of h of minus tau, e to the negative 2 pi f tau d tau. And now let's make a change of integral, change of variables. Let negative tau equal alpha. and this is integral from minus infinity to infinity, h of alpha e to the plus j 2 pi f alpha d alpha. All right, and this is the complex conjugate of the forward Fourier transform, and this is just that. All right, so if I take the Fourier transform of h of minus tau, I get the complex conjugate of h of omega. All right. Okay. So then, let's recall that the autocorrelation at the output was h of minus tau convolved with h of tau convolved with, autocorrelation of tau. If I take the Fourier transform of all this, this is going to give me, by the Wiener-Kinshine theorem, it's going to give me the power spectral density of the output, and that's just going to be h complex conjugate of omega times h of omega times power spectral density of x of omega. And my general result then is that the power spectral density of the output, when I take a function and multiply it times the complex conjugate of itself, I get the modulus squared times the power spectral density of the input. There's my other general relationship. Okay? All right, so you might compare this to if I was talking about a linear time invariant system with a non-random input. If we had a non-random input, let's say f of t, the output y of t is related this way. Y of omega, which is just the Fourier transform of little y, would be h of omega times f of omega, right? So Fourier transform in this case of little f equals capital F, and the Fourier transform of little y equals capital Y. All right? So if we have a non-random input, the spectrum of the output is related to the spectrum of the input by multiplication with the system transfer function. If I have a random input, the power spectral density of my random output is the modulus squared of the transfer function multiplied times the power spectral density of the input. Pretty handy. Couple of things to note. Typically, we'll find the autocorrelation of my output by first finding the power spectral density of the output and taking an inverse Fourier transform. Alright, so if I understand, if I have knowledge of my system impulse response, I can take a Fourier transform to find the transfer function. I can then find the modulus squared. If I know the autocorrelation of the input, I can take its Fourier transform to get the power spectral density of the input. Multiply those two together and get the power spectral density of the output. Inverse Fourier transform to find the autocorrelation of the input if I so desire. Okay? So let me end all of this by giving you a caution. I said earlier on that we wanted to get access to the mean squared value, autocorrelation, and power spectral density of the output, and from mean and mean squared we could then calculate variance or standard deviation. Alright, so let me just point out a common pitfall that I've seen in the past. The mean squared value of my output is indeed the autocorrelation of the output evaluated as 0, as it is in all cases. And this can be written as the integral of my power spectral density. Okay? This is normalized power. It's the power dissipated by a 1 ohm resistor. Plugging in my output power spectral density, my mean squared value can be written this way. Okay, that's the way we could do it. All right. Mean squared value, or my autocorrelation evaluated at 0, is not found the following way. Recall that my autocorrelation at the output equals running out of room. Remember that. That's a tau, not a 2. Okay? Let's fix that. Okay? The autocorrelation evaluated at 0 is not h of 0, h of 0, that is not a true result. Wrong, 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 wrong. You cannot convolve constants. All right? When I plug 0 in for tau, I get a value, I get a number, I get a constant. Likewise, I get a constant here, I get a constant there. All right? You can't convolve constants. The convolution step must come first. All right? Convolution must be performed first. All right, and then once you do the convolution, which is perhaps a nasty integral, then you can plug in for 0 value of tau and get the autocorrelation evaluated to 0. I don't suggest you do it that way. It's a common pitfall. I'd like to get access to both the mean and the mean squared value. From there I can get access to the standard deviation or variance. You cannot do it by starting, you cannot do it by starting with that relationship and just plugging tau equal to 0. You've got to do some extra steps. The best way to get access to it is right there. Okay. Well, that's all I've got for today. We have some general relationships for input and output characterization for time invariant linear systems that have at least wide sense stationary random processes at the input. As usual, if you have any questions about what I've done, please let me know, and I will answer any and all questions as fully as I am able, as quickly as I'm able to get to it. You all have a nice day. Bye-bye.